So we've seen that correlation and regression are helpful tools, and they're used a lot in statistics. In this section, we're going to look at some things to watch out for when we're using correlation and regression. And the first thing to look out for is outliers, because they can have a very strong effect on both the correlation value and the regression line. So for my first example, I'm going to use this online app. I've got the website here. I'm just going to go over to that app. So here I've got 5 points clustered at the bottom left of my graph, and I have a correlation value for those 5 dots of 0.4986, so very close to 0.5. Now what happens if I add I'll add a point, an outlier way up here in the upper right there. So that makes my correlation coefficient go way up. Now it's 0.9759, so that's a lot closer to 1 than we were before. And if we can look at the regression line here. So it looks like that adding that outlier had a very big effect on the correlation coefficient. Let's see what effect it has on the regression line. I can grab that point if I click on it and kind of drag it straight down. And you can see that the correlation coefficient stays pretty high. As I drag it down, it gets a little bit smaller and smaller, and then finally it gets to be negative. So just moving that outlier has a very big effect on correlation, and I can in fact get my correlation coefficient all the way down to negative 0.8301. So when I had my outlier up at the top right, I had a very strong positive correlation, but when I moved it down to the bottom right, now I've got a very strong negative correlation. So that outlying point makes all the difference there. So you really have to watch out for outliers in your data set. So let's go back to my slides. So another thing that we used regression lines for is predicting trends. But we have to be careful about extrapolating and making predictions that go beyond the data that we've collected. This can make you make a bad prediction. So just because the data fits a line over a small window of time doesn't mean that that trend will continue into the future. So let's look at a couple of examples of that. Here I've got a graph where I've got age in months of an infant, and then the average height for that age. So at 0 months, or a newborn has an average height of about 50 centimeters. And then I've got the average heights for everything up to 12 months. And I've added my regression line on here for those 5 points that I've got, and it looks like they fit that line pretty well. But what happens when I add the rest of my data points to fill this in? So what if I add the data points for 15, 18, 21, 24, 27, 30, 33, and 36 months? Are they going to continue to follow that line? No, they actually start to level off, which is what you expect. Children don't keep growing at the same rate for their whole childhood, so they kind of level off here, and we don't really follow that line very well after 12 months. So we have to be careful and not use the regression line to predict values that go beyond our data that we've collected. So if I was going to go back here, I could make a good guess for how tall a child would be at, say, 4 or 5 months. That would probably be pretty accurate if I just looked at my regression line there. But once I go out past 12 months, then it's not very accurate anymore. Here's another example. Here I've got the months of the year, so 1 corresponds to January and 2 is February and so forth. And I've got the average high temperature in degrees Fahrenheit for a town. So this is actually for Hanover, New Hampshire, so it's pretty cold. And the average high temperature in January is around 30 degrees. February goes up a little bit, still in the 30s. March looks like it gets up into the 40s, and then April it gets up into the 50s. So if I just use these 4 points and I drew a regression line, it looks like my temperature keeps going up all year. And we know that that's not true. Generally, for any town in the northern hemisphere, you're going to start out with low temperatures in January in the middle of winter. The temperature is going to rise until you get to the middle of the summer in July here. So actually we've got a pretty good fit all the way up until July, but then the weather starts to cool off again, and after that my temperatures start to fall. So it would be bad to try to predict the temperature for, say, October using this regression line. And the last thing we want to talk about is that association does not imply causation, or you may have heard the phrase correlation does not imply causation. So if we have an explanatory variable x and a response variable y, even if the correlation is very strong between those two, it's not by itself good enough evidence that changes in x actually cause changes in y. So to show that, we also need to demonstrate that we ruled out the possibility that the change in the response variable is due to any other variable or reason besides the explanatory variable. And we need to show that the association happens under a variety of conditions, and that we've got a reasonable mechanism or model to explain how x causes the changes in y. So let's look at some examples where correlation does not imply causation. So here I've got a chart that shows the family income of students who took the SAT, and then for each interval I've got the mean math SAT score of students whose family income falls in that interval. So for students whose family income is less than $20,000, their mean math score was 460. And you can see in my chart here that the score goes up as the income goes up. So does that mean, so here that is in a graph I've plotted the bottom value of my interval with the mean math score to come up with this chart. And I've drawn the regression line in here, and you can see that these are very strongly correlated. Everything is very close to my regression line here. But does that mean that just having more money means that you'll have a higher math score? So the correlation here is actually 0.98, so it's very high. But there's really no direct mechanism by which more money leads to higher scores. So if suddenly a student's family won the lottery, would you expect that their SAT score would be higher? No, that doesn't really make sense. But we can think about as other reasons why we see this trend. Families with higher incomes may have the benefit of better schools that their children attend, and they also have access to extra tutoring and test preparation that they can pay for. So having those things is probably a better reason why their mean math score is higher than just the money by itself. Finally, we've got a football example. Does running lead to winning in football? So for the 2010 NFL regular season, there was a correlation between wins and number of running plays, and it was moderately positive, about a middle correlation of R equal to 0.48. So does this mean that running causes winning? Well, what would happen if a team decided that running causes winning, so they're just going to run the ball all the time? That's probably not a very good strategy, and they're probably not going to win if they just run the ball all the time. So what's actually happening here? Well, once a team gets a lead in a game, they tend to start running the ball more often to minimize the risk of losing the ball and to run down time on the clock. So what's really happening is that once a team is winning, they start running more. So it's kind of the opposite of what we were saying here, that if you run more, you will win more often. But in reality, what's happening is that the team gets a good lead and then they start to run the ball more. So when they're winning, they run the ball more. So things to know for this section: you should know that outliers have a big influence on correlation values and regression lines, so you have to watch out for outliers. Predicted values from a regression line that go far beyond the range of collected data can be inaccurate, so you want to stay kind of within the window of where you've collected data. That association does not imply causation.